have here 4 pictures, and we're going to start by talking a little bit about each of them. This first one here we'll label picture number 1. Appears to be the wall of some quarry. Looks like, well, it's really hard to tell here, but looks like some blocky igneous material. Who knows if this is because of existing fractures and structures or because of blasting that the rock looks like this. You can see it's all on the ground here, right? So something's been going on there. In 2 here, we have 2 cores of what looks like some igneous rock material here. You can see the little crystal grains. Not sure exactly what it might be, but it's got a little bit of green, a little bit of brown, and a little bit of this pale material in here. Number 3 here, we have quite a nice looking, this would be a nice place to hike probably. You got this big sandstone outcropping here. Looks like a pretty consistent layer. It's dyed a little bit pinkish, it looks like. So maybe some iron in there. And then number 4, we have this kind of grainier picture here of this tunnel where we've got, I don't know, some igneous or metamorphic material probably. I don't know, very difficult to tell. But some old looking tunnel with no shotcrete, no rock supports. From the person standing back here, it looks pretty narrow. But having introduced these 4 pictures, the question now is, one of them is different from the others, and which one is that? Now, for the geologists in the room, it might be tempting to say number 3 because it portrays a clearly sedimentary rock, while the rest of them appear to be igneous or metamorphic or something. And if you thought of that, then props to you. But what we're actually looking for here is the distinction between rock and rock mass. And now when we go through each of them, number 1 we would say is a rock mass. Number 2 we would say is rock. Number 3 is rock mass, and number 4 is rock mass. So what makes number 2 different? Well, kind of the obvious answer here is going to be the scale of it, right? These are 2 small cores. We don't have a scale here, but based on the thickness of this cardboard, these things are probably about maybe 1 inch in diameter, right? Very small cores compared to an entire wall of a quarry here, an entire sandstone outcrop that towers above these trees or bushes here, an entire tunnel that encloses these people you see inside. So the scale is kind of the first and most obvious thing, and that's not to say that's all that's going on, but if we're to compare rock versus rock mass here, it's a good start. So I'll draw this out here. We'll write it up. Rock, compare that to rock mass. Rock mass contains the word rock in it, right? So you'd think they'd be quite similar. And in that same way, maybe you'd think that rock mass just contains a bunch of rocks. So rock, when we talk about the scale, it's usually going to be laboratory scale, right? It's something that you can slice out and specifically test. Like those cores, you could take them and, test whatever you want in them. You could look at the minerals contained within them down to a T. You could assay them for some sorts of metals or other materials. You could perform a UCS test on them if they're cut to appropriate dimensions. Any other mechanical properties test, Young's modulus, Poisson's ratio, triaxial compressive strength, whatever you want, right? But the scale is something that you can put in a laboratory versus rock mass is inherently in situ. And that's going to be 2 big differences here. And you'll see that it's incredibly important that we talk about the differences between these 2 from a theoretical perspective in the fields of rock mechanics, geological, and geotechnical engineering, because this difference here is inherently massive. Laboratory and in situ makes a huge difference, and the fundamental principle guiding this is that we cannot use what is present in the laboratory to accurately reproduce something in an in situ or in the field environment most of the time. We can glean certain interesting things from laboratory tests. You can do all of your regular mechanical properties on a rock that you have in the laboratory, right? To go back up to our pictures here, let's say that this is, well, I don't know exactly what rock type this is, but let's just make it easy. Let's say it's there's a core of a piece of granite that was taken from the northeastern United States, right? somewhere in there, very general. Maybe it was taken from a very specific formation that we know the exact extents of. We know generally where the water, the alteration, different altering factors are present, right? If we know something about that, then what we can jump in and do is test these very specific, the properties for this very specific rock type, right? So again, we could do something like the UCS, we could do the TCS, we could do Young's modulus, or what's the symbol for Poisson's ratio? Is that nu? I think it's nu, that little V thing. Pardon my poor writing with this pen here. Brazilian tensile, indirect strength tests, whatever you want. And then what we can do with that is make a very kind of scientific measurement, right? If we're looking at UCS specifically, right, then maybe we would cut the core to an appropriate size, grind it down, dry it, and then put it in a test cell, a hydraulic press, make sure we can record the stress as well as using extensometers or strain gauges to measure the strain. And then we'd have, you know, our stress strain curve that's developed. We would find where it breaks, call that sigma yield or sigma fracture, and record that as our UCS. And we could repeat that over and over in a very scientific process. This kind of standard, what you learn in, well, shoot, probably going back to 3rd grade, right? You can take a bunch of different samples and record them out and say, okay, we got some data here. Maybe some of the time it fails around here. Maybe some of the time it's much stronger with all these different samples. This will be our UCS on the x-axis, and this will be our frequency N on the y-axis. And you could develop a summary statistics from that, say x bar and sigma, to use kind of traditional probability and statistics symbols there. And once you know this, you can use that to predict things about the rock. If someone asked you, for example, to say something about the strength of a certain type of rock, maybe this granite that we've been talking about is present in an underground civil tunneling project, right? And they want to know, hey, we ran into this big unit of rock, and we want you, this guy who's being paid a lot, to tell us exactly what's going on here, right? Mr. or Mrs., excuse me, Mr. or Mrs. Geologist or geotechnical engineer or some other, you know, engineer role. Tell us about this. And you could go in and look at the literature and say, well, looking at the, you know, maybe you pluck out the UCS would be a great one. The TCS would be another good one. The strengthening factors, maybe how well it holds up under confinement, shear strength factors. You could look at these and say, well, on average, it's this, and the spread of the data tends to be this. So we should accommodate, you know, the worst case scenario, and maybe account for, you know, these weaker, what's the lowest area, maybe develop a confidence interval, right? You could go back to simple scientific and mathematical processes to make an informed decision about the rock. We're still talking exclusively about rock here. And you'll notice my tone has been very much that, yeah, we can work with it, right? The world is not that simple, though. If you just did that, if you just looked at the properties of the rock itself, you're missing a huge part of the picture, right? Because when we take a sample of this granite, right, or to go back to the picture to give you a really good visual, if we were to just look at these two pieces of core here, right, whatever this igneous material is, if we were just looking at these two pieces of core, right, how much material do you think is contained within them? I don't know. Again, if it's an inch in diameter, maybe it's a few inches of length being represented by this picture right here, that's not a lot of material. That is very little material. And then you start to say, well, if we're tunneling through this layer, you know, or this rock unit, all of a sudden we're dealing with a huge, huge, huge amount of material, a massive amount of rock. And you don't know, for instance, this core here, it looks pretty consistent. It doesn't look like there's any weird patches of alteration or any joint sets or fractures going through it. But you don't know what that might look like, you know, 5 feet in any direction, what's going on. Right? These were drilled out, and they were, hopefully the drilling program was done intelligently to try to intercept any big structures. But at the end of the day, we don't know the whole picture until we've developed into it, until we've moved the rock in order to get to this piece, right? And so that's where we make that clear distinction. This is a laboratory specimen. These are in situ. This is the real world, right? So when we get into, again, our rock mass here, it's that in situ. And again, we still have mechanical properties associated with it, but those are not what govern the strength of the material, right? There'll be a small part of it, right? This mechanical behavior, oh yeah, it comes in here, and we'll write down, maybe we're concerned with the UCS still. We say that's a pretty good delineator of whether a rock is generally competent or not, right? You could have, for instance, a very high UCS, granitic gneiss or something compared to maybe there's a much weaker limestone. But that same rock, maybe that granitic gneiss, is in a really bad structural zone where there's a lot of faulting, a lot of water inflow, versus the limestone could just be a very homogeneous unit, right? And this is where we start coming up with these modifying factors, these strength reducing factors that take place within a rock mass within the in situ environment that we simply can't account for if we're just looking at the rock type and what its theoretical strength and other mechanical properties might be. So again, modify it. And ultimately, these modifying factors are difficult to quantify exactly, but we can have things like the discontinuities, right? And you'll see that's a pretty general term for discontinuities. Got to make sure I can spell big words here. Discontinuities is a general term for things like joints, joint sets, faults, fractures, anything where you have one slightly different unit of rock touching another unit of rock, or the same unit of rock that's just been forced apart for something and maybe it's been altered around it, there's water in it, there's some other, clay, talc, something infilling within it, right? So discontinuities are going to be a big one. As a subset of those, so kind of in here, you might talk about the surfaces of them. Are they slick with water or some clay that's going to be really weak and shear that we have to consider? Are they generally, are they altered with some other form? Things like this. So alteration, you're going to care about the spacing of these discontinuities, right? Are these discontinuities, do they break the rock up into a few big blocks like this, where it'll be easy to kind of, if you put a bolt in there or something to pin them together? Or is it going to be this big, nasty, broken mess of rubble when you're tunneling through it? And again, I'm just using the tunneling example here because it makes a good, it's kind of easy. But anytime you're dealing with in situ rock masses, this is going to come into play. Surface, underground excavations, doesn't matter, right? So all of that has to be considered. Groundwater, again, GW, groundwater, our good friend. Water is good for life, but almost never good for, underground workings. You have to deal with it, you have to pump it, and of course it weakens the rock itself. It makes it more slick and ready for shear failure. And then again, things like orientation, right? What's the strike and the dip of different structures that are cutting through it? There are all these things, right, that are going to weaken the strength of it and make it worse for the people who have to be concerned with tunneling through this. So all of this has to be accounted for, and it's very difficult to do with just, if you're planning an excavation, a tunnel, right? Maybe you've done quite a bit of exploration drilling ahead of time, but it's very difficult to make an informed decision just based on rock core like this. So a lot of times what you'll see is kind of a continuous monitoring of the rock quality, the rock mass quality, I should say, as excavation progresses through it, as it's tunneled through, as it's mined through, as earth is removed around it. And so we have multiple systems then that kind of assign scores to rock mass. And here's where, like I said, it becomes much less scientific like this over here in like rock, and much more empirical and data driven. You'll have these systems that basically just err on the side of being very, very conservative most of the time. So you'll see ones like RMR, that's rock mass rating system, and another popular one is going to be the tunneling Q index, which I believe the Q stands for quality. I'll have a video on the two of these just because they are interesting to look at, and I think understanding both of them gets you a good breadth of knowledge on how we deal with rock mass when it's not of consistent quality. And really, again, the big thing is the data is going to have a massive spread, right? If we're trying to correlate things like, RMR, some arbitrary score, with the probability of failure, right? Ultimately, what we're trying to do is aggregate all of this into a score and see the effect of it, right? To some extent, even if it has a high UCS, if it's faulted to an extreme degree, it's no good, right? Or even if it's very strong rock, or even if it's, very homogeneous rock, but the rock itself is a very weak unit, then all of a sudden it's not going to be able to support itself around an excavation. These things have to be accounted for. And so these systems aim to aggregate the material, all of this material, into one score. And so what you'll see is, again, this conservative estimate where, if you look at all these different factors and probability of failure, we'll label that, right? If this is the probability that an excavation, fails, or a wedge comes down or something like that, you'll generally see, a fit that tries to encapsulate all of the data above it, or, probably below it. You want to overestimate you want to underestimate the strength of the rock, the ability of it to support itself, and deal with that accordingly, right? In a tunnel, that might influence the way your drilling and blasting pattern, or if it's being cut by a TBM, that'll inform the decision on what kind of machine you're using, how your ground support regimen comes into play, right? All of these things. So really, that's kind of the big picture thing here. If you're looking for one big takeaway, it's going to be that rock is, generally speaking, rock is good and generally predictable, and then rock mass is going to be not the polar opposite, right? We still work around it, but it's going to require much more work. And that's an important thing to understand, right? For people who are just kind of starting off, right? Especially if you've been exposed to, if you're taking a rock mechanics course or looking into it, you've probably dealt with adjacent fields. Let me finish writing here just so I don't forget. A little bit all over the place here. Bad and unpredictable, but not to the extent that we can't deal with it. But as I was saying, just to kind of round this out, if you're taking a rock mechanics course or you're interested in the field, then you've probably been exposed to, things like material science and statics, things that give you a precursory understanding of things like stress and strain and forces and things that are being held in static equilibrium, as well as the properties of material. And there's kind of this student's desire for things to be very simple, right? And that's the way it's going to be in something like an engineered materials course, where, steel, if you manufacture it right, then you can look up the properties of a certain type of steel, pick whatever you're looking for, and they can tell you, it's going to be an average strength or whatever property you're looking for, and there's going to be some spread, but generally it's going to be pretty small, and you can make really well-informed and competent designs around that, right? And so you can really do a good job at kind of zeroing in on the optimization between something like a cost and a safety factor. Here it's much more difficult. And some of these systems that we talk about, that I'll make a video on in the future, aim to kind of rein it in. But ultimately, really, there's just so many variables at play. And that's maybe the biggest takeaway. When you're big, there's just more uncertainty. The more rock you have, the more uncertainty you have. And I think I've gone on enough about that for now. No math in this video. Isn't that nice for rock mechanics? Last time we dabbled in a little bit of calculus, which, enjoyable maybe. But this time just entirely kind of theoretical stuff. We'll get into some basic math when we talk about RMR and Q. Those are just kind of, one of them's additive and one of them is multiplicative. but they should be pretty intuitive, and they use kind of very similar systems in how they work. But that is enough for now. I've gone on long enough. Hopefully this was of some use to you, and we'll see you next time.